Hello everyone. So in today's lecture we will talk about admittance and impedance, and those are concepts that are equivalent concepts that are equivalent to resistance in the DC domain. So in the DC domain, in DC circuits, essentially we have the concepts of resistance, which relates the voltage to the current, right? But we said in the AC domain now, in AC analysis, we don't work with voltages and current directly. We work with the phasor representation of a voltage and the phasor representation of a current, right? And then there's a relationship between them, and that relationship is described using impedance, which is the analog of resistance, and admittance, which is the analog of conductance, right? So essentially, if we have any circuit and we look at it, we take two ports from the circuit. Circuit is a black box. It doesn't matter what's inside it, but in DC analysis, we discovered, hey, if I have any voltage supply that I apply, and then I measure the current going in, right, then the resistance of the circuit is going to be V over I, right? This is as far as Ohm's law in DC analysis. So this is DC analysis, right, and this is Ohm's law, right? The resistance of now this could be a single resistor, this could be like a bunch of the big circuit. The point is that the equivalent resistance of this big circuit is going to be V over I, right? So in the same manner, in the same way that we do DC analysis in this way, and we just look at two ports at a single interface to a circuit, and we apply a voltage and we check what the current is, and the ratio of the voltage and the current is the resistance. Same thing, we could inject a current and measure the voltage, and the ratio of those two is going to be the resistance. In the same manner, in AC analysis, we could do the same thing, right? So we could have a circuit, general circuit, black box, and then we have the two ports, and then we inject an AC voltage, a sinusoid, and we represent it using phasor representation. So it's a V phasor, right? And then we measure what current we get, I phasor, right? Then the impedance of the circuit is defined. Remember, impedance is the analog to resistance in the AC domain, or in the frequency domain, so to speak. So the impedance is defined as Z equals V phasor over I phasor, right? Using the passive element convention. What's the passive element convention? When I measure V across, so if I measure V across the circuit or element like this, I will be going in, right? So if I have an element like this, and I measure V, and then I need to measure I in this direction to get Z, right? So Z equals V over I, and the sign convention needs to follow this form. So this is the passive element sign convention. Okay, this tells you what direction is the positive convention for a positive current, right? And what's the relationship as far as the signs is between the voltage and the current. Okay, so this is the definition of impedance, and it's a complex number. Impedance is a complex number. It's the ratio of the V phasor over the I phasor. It is not a phasor, though, right? It's not a phasor. A phasor has a very specific meaning. A phasor is a complex number representation of a real-time signal. It's a representation of a signal that is a sinusoid with respect to time, right? Of either a forcing function or a response. So the phasor represents either a forcing function or a response that is a sinusoid. Impedance is not a response or a forcing function. It's just a relationship between two signals. That's what it is. So it is a complex number, but it is not a phasor, right? So so when we calculate it, it's just, V phasor is a complex number, so it has some magnitude, and then theta V over I phasor has some magnitude, and then theta I, right? So the evaluation of Z is just going to be Vm over Im. Angle is going to be theta V minus theta I. I could write this as Z magnitude, or I could write this as Zm, same thing, right? And then angle theta Z. So it's a complex number that has a magnitude and has a phase. In rectangular form, I can write this as Z, and then I'm going to put in omega here to emphasize that the impedance in AC analysis is going to depend on the frequency. We discovered that for the inductance and the capacitor, right? The value, the relationship between V and I depending on the frequency, right? It looked something like this, J omega L and 1 over J omega C, right? So we'll discuss that in a bit. But if I want to write J omega in rectangular coordinates, it would look something like this, R omega plus J x omega. That's how it will split into a real part and an imaginary part. And the real part is what's called the resistance. Right? And it turns out to be a resistance. If your element is just a resistor, your impedance will only have this part, the resistance part. It will not have the imaginary part. The imaginary part is called the reactance. It's the imaginary component of the impedance. Okay? What's the relationship between the impedance and R and X is the same as the relationship between the polar form and the rectangular form. It's easy to calculate, right? Theta Z equals R plus JX, right? So magnitude Z is just R squared plus X squared, the resistance squared plus the reactance squared, and then the angle of the impedance is just tan inverse X over R, right? You could also write that R equals Z cosine theta Z, and X equals Z sine theta Z. Okay, so yeah, so those are the concepts that are important in the study of impedance. So we could describe the impedance for any general circuit. What is the impedance for the basic passive elements? What's the impedance for R, let's say? When I take R, I apply a voltage to it, I get an I through it, right? And we found out last time that V equals Ri, right? So that means that for R, remember Z is the ratio between V and I. So for R, Z is just R, the resistance. Z has pure real component, does not have an imaginary component. For L, Z we found out last time was J omega L. So that means that XL, the reactance for an inductance, is omega L. The resistance for an inductance is 0. It has no resistance. The real part is 0 for an inductor. Right, so we did this, recall the last lecture, we did this last time. We found the relationship between V and I for an inductor. So this is V, and this is I. Okay. For a capacitor, we also found that last time. The relationship between V and I for a capacitor turned out to be, so let me do it quickly. So this is a capacitor, and then this is I, right, and then so it's V dV. For a capacitor, I equals C dV by dt, and then I put in the phasor form and put in the implicit EJ omega t equals C phasor form, implicit EJ omega t. I'm just redoing it for reference. Right, so this is going to be I phasor, EJ omega t equals V phasor, J omega, oh, there's a C here. j omega c e j omega c, omega t, e j omega t cancels. So I end up, oh, there's a vm, v here, right? So we end up with v equals 1 over j omega c I. So this is the ratio of the voltage over the current. This is the impedance. The impedance is going to be 1 over j omega c, which I can rewrite as minus j over omega c. So this tells me that the resistance for a capacitor is also 0, but the reactance for the capacitor is minus 1 over omega c. Right? So those are the impedances for the basic passive elements. If we have a more complicated circuit, we will get an impedance that's not just simply like that. It will be a complex number, but it will be kind of like a combination of those R's, L's, and C's, which brings us to the point of how do we combine impedances. Turns out the way we combine impedances is exactly the same way we combine resistances. And resistances in DC analysis, we know how to combine resistances in series and resistances in parallel, right? We know how to do that. And really those relationships that we discovered in DC analysis arise from KVL and KCL. That's it, right? Those KVL and KCL relationships still apply in AC analysis when we're dealing with phasors. Because they still apply in AC analysis when we're dealing with phasors, we still get the same relationships for impedances in series and in parallel. So you could have a bunch of impedances, elements or parts of circuits that have a certain impedance. You calculate certain impedance for them, and if you string them in series all the way up to Zn, right? This equation still follows. Zs equals Z1 plus Z2 all the way to Zn. And then if you string impedances in parallel, so you start from Z1 up to Z2 up to Zn, right? So then the equivalent impedance of stringing them in parallel, we know the formula. It will be the same formula as in DC analysis. So 1 over Zp is going to be equal to 1 over Z1 plus 1 over Z2 all the way to 1 over Zn. Right? Those relationships arise from applying KVL and KCL. And KVL and KCL still apply for circuits represented by phasors. Right? Because they still apply, those relationships still apply. Recall that the key way of deriving those, the key method of deriving those relationships is as follows. So we have the total voltage, right, plus minus V series, right, and then I have the voltage across each element, V1, V2. KVL specifies that V series equals V1 plus V2 all the way to plus Vn. But then the Ohm's law in the AC domain specifies that Vs is just Is times Z, right? Z series, the total impedance, right? So Ohm's law still applies with the use of phasors and impedances. And then V1 is just the same current. When you string them in series, Is is the same current that flows through all the elements. So the current would be the same for each VI. I can take it out, and then each VI will have its own impedance, Z1 plus Z2 plus Zn. And then you just divide this by this, and we get the formula. Same thing for the parallel situation. The key here is applying KCL. So the key is that the voltage is the same. So V parallel will share the same voltage. Those are all phasors, by the way. Right. So applying KCL. So this is I, right, parallel. Right. So I parallel. This is I1, I2, and using KCL, I parallel is just going to be I1 plus I2 all the way to IN, right? How do I get from this current a voltage? I multiply each one of those by an impedance, right? So if I multiply this by, no, sorry, what, from Ohm's law, what is V? V equals Z I. So I will always going to be V over Z, right? So IP is going to be, the total current is going to be just V parallel over Z equivalent, the total impedance of the whole thing, right? But this equals also V parallel. The key thing here is that the voltage is going to be the same for all the elements. In the series case, we used the fact that the current is the same for all the elements. Here we're using the fact that the voltage is the same for all the elements. So for I1 is going to have Vp over Z1 plus Vp over Z2 and so on. We end up with Vp over Zn. We cancel, divide out Vp, right? So I end up with 1 over Zp equals 1 over Z1. Right? Remember, those arrows, those are not vectors. Perhaps I'm using confusing notation, but that's fine because we don't use vectors in circuit analysis. When I use those arrows, when I'm writing stuff, I mean phasors, right? When you look at your textbook, they used the bolded form. So phasors are in bold form, bold font. So this is how you derive the relationship for the parallel connection of impedances. Okay. In all of this, the units for impedance was what? Ohms, right? It has to be ohms, right? Because Z is defined by as V over I. Right? It has to be voltage over current, so it has to be ohms. Now, in a similar way where we defined R as resistance, and then we had the inverse of R, G, which is conductance. So in the similar manner, we will define an inverse of Z. So if I have Z, which is impedance in AC analysis, which is the analog to R, the inverse of Z is what's called admittance, which is the analog of conductance in DC analysis. Admittance. Right? And admittance is defined as follows. It's the inverse of Z, which means it's I phasor over V phasor, and it has units of Siemens. So it's analogous to conductivity. Okay. The same way we can write Y as Y magnitude, theta V, right? And in rectangular coordinates, we write it as G plus JB. So G, the real part, is the conductance, the same as the conductance in DC analysis, and B is the AC part, or the imaginary part, which is called the susceptance. Okay. So in Z we had resistance, reactance. In Y we have conductance, susceptance. Right? And then we can relate the rectangular form of both together. So G plus JB, which is the admittance. If I invert it, I get the impedance, right? Or it's the inverse of the impedance. So it's the inverse of 1 over R plus JX. So this allows me to relate G and B to R and X, right? So this equals R minus JX over, so I did just R minus JX over R minus JX. That's all I did, right? To get the complex conjugate of the numerator so that I get a real value at the denominator, right? So I end up with the R minus JX over R squared plus X squared. So I can equate this to this, and I end up with G being R over R squared plus X squared, and B equals minus X over R squared plus X squared. Okay, so notice in general, the inverse of the resistance is not the conductance. The inverse of the resistance will be the conductance only if x is 0. So if x is 0, I end up with r over r squared, so I end up with 1 over r. Right? So for AC analysis, the inverse of the resistance is not the conductance. The inverse of the resistance is not the conductance. The conductance is actually this formula. It depends on both the resistance and the reactance. That's rather a weird fact, right? And the susceptance, the inverse of the susceptance is not, the inverse of the reactance is not the susceptance. Only if the resistance is 0 do we get 1 minus 1 over x, right? So the inverse of the reactance does not directly give me the susceptance. It's this formula. The resistance plays a part, right? And then R, I can also compare R, right? R, I can do the same thing. I can move those things around. I can move this up here and this down here and then do the same thing, and I end up with R equals G over G squared. You can do it, right? It's very simple. There's nothing different. And then X equals minus B over G squared plus B squared. So in general, the inverse of the conductance is not the resistance unless B equals 0. If B equals 0, then R, the inverse of the so I end up with G over G squared, 1 over G, then the inverse of the conductance and the resistance. And also if B equals 0, I end up with the negative inverse. Oh, sorry, if G equals 0, if the conductance is 0, I end up with the negative, I end up with minus B over B squared minus 1 over B. I end up with the negative of the susceptance, negative inverse of the susceptance being equal to the reactance. So notice in the relationship between the reactance and susceptance, there's a negative sign, right? And this inverse law does not only applies when G equals 0, right? Same thing here. Only if x equals 0 can we write G equals 1 over R, and only if R equals 0 can we write B as minus 1 over x. Okay, but those are the general relationships between GB and Rx. Okay, for our regular passive elements, resistance, inductance, capacitance, we can do the same thing, right? So for a resistance, there's just there's just G component, right? There's no imaginary component, and this equals 1 over R, right? This is the admittance. This is YR, the admittance for a resistor. The admittance for an inductor is the inverse of the impedance, which is 1 over J omega L, which is minus J over omega L, right? So B for an inductor, BL, is going to be minus 1 over omega L. For a capacitance, we found that the impedance is 1 over J omega C. So the admittance has to be the inverse of that. So it's equals J omega C, right? So the susceptance for a capacitor is omega C. Okay, so nothing different about the admittance. It's just the inverse of the impedance. And then we can derive equations for series connection and parallel connection of admittances. So we have a bunch of seriously connected admittances, right? IS is the same, right? So IS is the same, but I have V1, V2 all the way to Vn, right? IS is the same along the board, and let me write actually VS total using KVL is just V1 plus V2 all the way to Vn, and then using admittance I can write VS as IS. Oh, yeah, I can write, so using admittance, what's using admittance? We said admittance equals I over V, right? So V equals I over Y, right? So Vs is going to be Is over Y series equivalent, the equivalent impedance, which equals V1, which is going to be I1, which is the same as Is, the kinds are the same, over Y1 plus Is over Y2. This is the voltage across each element, plus Is over Ym. So we end up with this formula for admittance. 1 over Ys, or 1 over Y total, equals 1 over Y1 plus 1 over Y2 all the way to 1 plus Yn. So the relationship is inverse to that of impedance. In impedance, the series connection is just a summing up of the impedances. When we have series connection of admittances, we get a relationship akin to the parallel case for impedances, right? And then the same thing for parallel connection of admittances. We get the relationship that's akin to the series connection of impedances. So I have Y1 up to Yn, and then the voltage is the same, Vs across all of those, right? But then I use KCL and I say that Is equals I1 plus I2 all the way to In, but using Ohm's law in phasor form, I know that each I equals Y times V, right? So Is equals Vs times Vs times Y equivalent, Y parallel. I1 equals just Vs, the same voltage, times Y1. I2 equals Vs, the same, all the voltage is the same. The voltage is the same across the parallelly connected elements, times Y2 plus Vs times Yn. So I cancel out Vs and I end up with the formula Yp equals Y1 plus Y2 up all the way to Yn. Right? So in the case of admittances, parallel connection of admittance, if we have a parallel connection of admittances, we just sum them up. In the case of impedances, if we have a series connection of impedances, we just sum them up. For the other form, we have for impedances, if we have a parallel connection, we sum up the inverses. For admittances, if we have a series connection, we sum up the inverses. Okay. One big fact here I want to state is that Z and Y are functions of frequency, omega. So notice for the capacitance and the inductors, the value of Y and Z are functions of frequency. If you have a different frequency, you'll have different impedances and admittances, right? So really in AC analysis, the response of the circuit, that's how we factor in that the response of the circuit in AC analysis is going to depend on the frequency. It's going to change with the frequency. Response of the circuit in steady state. And we factor out that frequency dependence by noticing that Z and Y are functions of frequency. Okay, that opens the door to frequency, what's called frequency analysis, where we examine how the behavior of the circuit or the characteristics of the circuit vary depending on the frequency. Okay. All right. Let's do some examples. So we have a voltage source. In the time domain, it's 50 cosine omega t plus 30 degrees. As a phasor, it can be written as 50, 30 degrees. And it goes into a series R, L, C circuit. Right, so what we're trying to solve for is the impedance of the circuit at 60 Hertz and 400 Hertz at two different frequencies. So at 60 Hertz, the impedance of the resistor is just 25 ohms. The impedance of the inductance is j omega L, which is j omega is 2 pi f, 2 pi 60. And then L is 20 millihenry, 20 times 10 to the power minus 3. If we do the math, this turns out to be J times 7.54. Right, and then the impedance of the capacitor is 1 over J omega C, which is minus J over omega is 2 pi 60, and then C is 50 microfarads. Again, if you crunch the numbers, we get minus J 53.05. The total impedance is going to be the ZR, they're all in series, right? So it's going to be ZR plus ZL plus ZC, which is 25, minus minus 53 plus, it's going to be minus J 53.05 plus J 7, which is going to be minus J 45.51 ohms. Okay. If we wanted to calculate the current is just, as a phasor, just going to be V over Z. It's going to be 30 degrees over 25 minus J 45.51. We don't want to do this calculation. We just turn this into its polar form to facilitate division. So I end up with 30 degrees over, if I find the magnitude of this number, I find it's 51.92. The phase is minus tan inverse, is tan inverse minus 45 over 25, which is minus 61.22. If I take this angle to the numerator, I get a positive angle, plus 30, I get 90. So I, as a phasor, is going to be, and 50 over 51.92 is almost 0.96. Right, so I, as a phasor, is going to be 0.96, 91.22 degrees. We can write this in the time domain as 0.96 cosine 2 pi 60 t plus 91.22 degrees amps. Okay. What if F is 400 hertz? Okay, the impedance is going to be different, right? Because as we calculated, the impedance is dependent on the frequency, right? So if we do that, ZR is going to be the same, 25. ZL is going to be 2 pi, now 400 instead of 60. 20 times 10 to the power minus 3, which is equal to J 50.27 ohms. And ZC is equal minus J over omega C, which is, if we do the number crunching, is going to be minus J 7.96 ohms. Right? So the total impedance is going to be the sum of those three, which is going to be 25 plus J 42.31, which is in polar form equal to 49.14, 59.42 degrees. Notice something curious happening here. When at 60 hertz, the total impedance has a negative reactance. Negative, meaning X is less than 0, right? So when does negative reactance occur? Negative reactance occurs typically when we have a capacitor, right? And we have something that's equivalent to a capacitor, because the capacitance has an impedance of 1 over J omega C, which is equal to minus J over omega C. So we say that the reactance is capacitive in this case. Right? But if we change the frequency, the characteristic of the circuit changes, meaning now that the reactance is positive, X is larger than 0. When does typically X have a reactance larger than 0? When the circuit is behaving like an inductor, meaning when the reactance is inductive. So here we've shown that depending on frequency, the reactance is going to either be capacitive, meaning X is less than 0, or the and if we change the frequency, the reactance might turn from reactive, from capacitive to inductive, meaning X is larger than 0. Okay. But if we have this circuit, so I have voltage that as a phasor looks like this, 60, 45 degrees, and then I have this circuit, 2 ohms, and then I'll write the impedance right away here. I won't do 2 pi, I'll just write it right away, J4, right? Yeah, so this 4 is the result of 2 pi 60, which is omega L. Right? Sometimes you see impedance given at a certain frequency directly, right? So they don't give you L, they just give you the result of 2 pi 60 times L. Right? This is at 60 hertz. If the frequency changes, this value needs to change. Right? So we want to find the equivalent admittance, YP. Equivalent admittance is just they are in parallel, so it's going to be just the sum of the admittances. The admittance of the first element, the resistor, is going to be half the reciprocal of the resistance. This is impedance, ZL. And then the admittance is the reciprocal of the impedance, so it's going to be 1 over J4. So I end up Siemens. So I end up with half minus 1/4 J Siemens. Right? I, what is the current in this case? Flowing into the circuit, I is just going to be the admittance times Vs. Admittance is half minus J quarter times 60, 45 degrees. Right, and this is, I want to do this multiplication, so I have to turn this into polar form. So this will be 0.559 minus 26.57 degrees times 60, 45 degrees. Sum the angles, multiply the magnitudes, I end up with I equals 33.54 as a phasor with an angle of 18.43 degrees. Okay. And so this is pretty straightforward. We're just reusing techniques that we already know from circuits 1 to calculate equivalent impedances and admittances. Another example, let's say we have this circuit, 1 ohms, and I'm giving you the impedance for every element directly. So this has impedance of minus J2 ohm. Yeah. So the capacitor, as I've said, as I've hinted at in the previous example, from the expression for the impedance of the capacitor, the impedance of the capacitor will always be negative, will always be imaginary and negative, while the impedance of an inductor will always be imaginary and positive, has to be. If you see a capacitor and a value given that's positive, imaginary and positive, that tells you that they're giving it to you as an admittance. Because when you take J and you take 1 over J, that turns it into minus J. When you take minus J and take its inverse, that turns it into J. Okay. Right. So we want to kind of like find the equivalent impedance of this Z equivalent of this kind of involved circuit. So it has multiple elements. 2 ohm, J6 ohms, and then a capacitor which is minus J2 ohms. Then I have here 4 ohms, J2 ohms, an inductor, and then something like this, J4 ohms, then a capacitor minus J2 ohms. Okay, so such problems, all we need to do is divide and conquer. So we want to first find the equivalent impedance of this thing, right? So we can first convert everything to admittance because it's parallel. Anything in parallel, it's easier to find its equivalent admittance. Anything is in series, it's easier to find its equivalent impedance, right? So the equivalent admittance for this is going to be let's see, it's going to be 1 over J4 minus 1 over J2 Siemens. Right, so the result is going to be, I take J upstairs, so this becomes minus J quarter plus J half Siemens. This ends up being quarter J Siemens. Okay, so what is the impedance in this case? The impedance is going to be, invert this becomes minus J, inverting J gives me minus J, and this becomes minus J4 ohms. Okay, so this here element, those two series, this parallel connection of an inductor and a capacitor has an impedance of minus 4 ohms. So now I sum it, minus J4 ohms. I sum it with those two. So the total impedance of this branch is going to be 4 plus J2 minus J4. So it's going to be what? So minus J4 plus J2 is going to be minus J2. So it's going to be 4 minus J2. Okay, so this whole thing, this whole branch, I found its impedance to be 4 minus J2 ohms. What about this branch? Well, I mean, this is also easy. This is 2 plus J6 minus J2, so it's 2 plus J4, right? So now this branch and the other branch here are in parallel, right? So we need to turn those two into an admittance to sum them up. 1 over 2 plus J4 plus the admittance of the other branch, 1 over 4 minus J2 Siemens, right? So that gives me, so I need just to sum this up. When I sum this up, I mean, that's easy. I just have to invert those. So I just multiply this by 2 minus J4 and multiply this by 4 plus J2 and turn it, move it to the numerator, and then, do the whole thing of inverting complex numbers. When I do that, I get this result. I get 0.1 minus J.2 plus 0.2 plus J.1. So I end up with the result being 0.3 minus J.1. I invert Siemens. I invert this now to get the impedance. Right, when I invert this, I get 3 plus J1 ohms. Okay, so I found the impedance of this whole thing, that direction. Now I need to sum it up with the impedance of this branch. Again, two parallel, right? So this is going to be what? It's going to be 1. Inverse of 1 is 1. Inverse of this is going to be plus J half, right? And I need to invert it, Siemens, to get the resistance. The impedance is going to be 1 over 1 plus J half ohms, right? So if I take this and I sum it with this, I won't do it, but you can do it easily. The result is going to be 3.8 plus J.6 ohms. So this is the equivalent impedance to the whole network. The point is that you're not doing anything different than what you did in circuits 1. You're only doing it now with complex numbers that represent impedances and admittances. Right, let's now do some examples with that involve phasor diagrams. Okay, so I want to start with the parallel RLC circuit. So we have some current presented in the phasor form. Then I have the voltage across the three parallel elements, right? Then I have a resistor, inductor, capacitor. Of course, because it's a parallel circuit, the voltage is going to be shared and the current will be different in every branch. So I have IR, phasor, IL, phasor, and IC, phasor, and then the impedance of the inductance, of course, is J omega L. The impedance of the capacitor is 1 over J omega C. Okay, so we want to draw a phasor diagram for this circuit. So the phasor diagram is something that occurs on the complex plane, of course. And there's always, a choice when you're drawing phasor diagrams about specifying which signal has a phase of 0, right? And it's a choice. I could designate I to be the signal that has a phase of 0, or I could designate V to be the signal that has a phase of 0. Since V is the common signal to all three impedances, it's easier to set V as having a phase of 0. So V is going to be Vm 0 degrees. Okay, so it's just a matter of selecting a reference that has 0 phase. It's a matter of choice. I could have selected IS to have 0 phase. That's fine. Okay, but it's better to select V in this case because V is common to the three impedances, and I can relate the current in each branch to V. So let's say V has a phase of 0. So this is V. Okay, so the total current going into the circuit is going to be a sum of three currents. It's going to be a sum of IR. IR is going to be always in phase with B, right? So this is IR, phasor. IL is going to be what? Is going to be V over J omega C, right? So IL is going to be V, and then of course V is Vm with an angle of 0 over omega C, and then this is going to be minus J in the numerator, which is an angle of minus 90. So it's going to be minus 90 degrees, right? So IL is going to be at an angle of minus 90 degrees. And then the same manner, IC is going to be at an angle of plus 90 degrees because IC is going to equal V over 1 over J omega, or this is J omega L, sorry. 1 over J omega C, which is J omega C V, which is going to be omega C Vm 90 degrees. Okay, now the total current IS is going to depend on the values of IR, IC, and IL. And two things could happen. Either so IC and IL are functions of omega. IR is not a function of omega. So omega could be such that IL, the magnitude of IL, is larger than the magnitude of IC. In that case, the phasor diagram is going to look like this. So I'm going to draw the complex plane axis again. So I have V, I have IR, and then IL is larger than IR. So the sum is going to look like this. It's going to be IL plus IC is going to go negative, and then IS is going to be this sum of the two vectors. So this is going to be IS. Okay, so this is what the phasor diagram would look like. If omega is such that IC is larger, magnitude is larger than IL magnitude, then we are going to get this sort of phasor diagram. So this is the reference V, this is IR, and then I sum IL and IC, but the sum goes positive. So I have IL plus IC, and the sum is this, IS. Okay, and can write it IS equals V over R plus V over J omega L plus V over 1 over J omega C, which equals Vm over R plus Vm over omega L, and this 1 over j becomes minus 90, angle of minus 90 degrees, plus Vm omega c, angle of 90 degrees. Okay, so this shows me that depending on omega, the is going to be on the in this upper right quarter of the plane, or this lower right quarter of the plane. Okay, so if we vary omega smoothly, meaning take omega from 0 to infinity, we will end up with such a situation for is. So this is going to be v. We said if omega is small, we will be somewhere around here. This is is1. But as we increase omega, is will start changing like that, right? Until we hit a point where is will be completely real, right? And then it's gonna flip positive, right? So I can, right? So this is how the phasor, so this is gonna be isn. This is how the phasor is gonna change for is as we increase the frequency. There is a point where the phasor for is is gonna be completely real, and there won't be any imaginary part. We can see that when we calculate is is going to be, 1 over r plus j omega L, sorry, j omega c plus 1 over j omega L v, right? That's what it is. And we can manipulate this, so we end up with 1 over r plus j omega c minus 1 omega L. Clearly, there is a certain frequency where this term goes to 0. Such a frequency exists, right? I just have to equate, I just have to set omega c minus 1 over omega L, this is L, write this properly, equals 0. I solve this equation, I end up with omega c equals 1 over omega L, omega squared LC. I don't know why I write my c's as if they are L's. My L's as if they are c's, okay? Equals 1, so omega is going to be 1 over square root LC. So this is the frequency where is is going to be purely real, where kind of like we can say that reactance of the inductor cancels out the reactance of the capacitor, and we end up with just real resistance. Okay. Another example of a phasor diagram is one with the series connected circuit. So if I have Vs, and drawing phasor diagrams is a skill that you need to develop. So hopefully we will do that in future homework, but this is a skill you are expected to develop and be comfortable in. Right, so let's do it for a series circuit. So I have here R, let's say 4 ohms, L 15.92 millihenries, and then C 1326 microfarads. Okay, now we apply KVL, right, because it's a series connection, so we know Vs equals VR plus VL plus VC. What's the common signal here? The common signal is the current, right? The current, same way as in the parallel case, the voltage was shared between the 3 elements. Here in this case, the current is shared between the 3 elements. So when drawing a phasor diagram, one good option we have is to use the current IS as the reference phasor, as the phasor that is at angle 0. We don't have to, but that's an option we have, right? And I can write VR as just IS R plus omega L. VL is just omega L IS. I had the J here, right? I'll turn J into 90 degrees, so it's going to be 90 degrees, right? So this is 90 degrees extra to the angle that IS has, plus I phasor over omega C minus 90 degrees. Okay, instead of IS, I could say like IS magnitude, because I'm considering I to be the reference phasor, so it has zeroed angle. Okay, so looking at this equation, I see that this represents the voltage across the resistor, this represents the voltage across the inductor, this represents the voltage across the capacitor. Voltage across the inductor has an angle of 90 degrees, VL. Voltage across the capacitor has an angle of minus 90 degrees, VC, and then this is VR, which is in phase with IS. Okay, so this is the phasor diagram. Let's draw it if VL, if we're in a situation is omega is selected, such as VL is larger than VC magnitude. So in this case, the phasor diagram will look like this. This is IS, this is VR. This is going to be, because VL is larger, the sum is going to be up like this in the positive region. And then the sum VS is going to be this phasor. Right. With the parameters given here, I mean, I'm giving you those special parameters. If you do the calculation, it turns out that the angle is going to be 45 degrees here. Okay. But what if, suppose, let's say someone told you, hey, I mean, let's draw the phasor diagram with, let's assume that Vs is the reference. And furthermore, Vs is not just a reference assumed to be at 0 degrees. Let's assume that Vs is a particular signal. So Vs, let's assume, is just 12 square root of 2, 90 degrees. That's what Vs is. So Vs is 12 square root of 2 cosine omega t minus 90 degrees, plus 90 degrees. Right? This is the particular signal that Vs is. I've fixed it, and I want Vs to be the reference. Right? So, so all we need to do is, with that Vs, let's calculate I. So we calculate I for that Vs, and I for that Vs turned out to be 3, you can do the math, 45 degrees. Just take Vs and divide it by R plus j omega L plus 1 over j omega C. That's all you need to do. And you end up with this I, right? So remember here, we want to redraw this phasor diagram. But this is the phasor diagram assuming IS is the reference at 0. But now we with this new reference, with Vs fixed to this value, we calculated that Is needs to be this, right? All we have to do now is shift the reference Is by 45 degrees so that it matches its actual Is. So the phasor diagram in this case is going to look, it's going to be exactly the same thing, only with Is shifted 45 degrees. So we end up with the same thing, VR, VL, VC, VC smaller than VL in this case, and VS is going to be, so it's 45 degrees plus the actual 45 degrees between I and VR and VS. So we end up with VS being there. So you can always shift the reference. You can always draw the phasor diagram for some reference, right? So this is I. You can draw everything with respect to some phasor set as a reference. But then when you can at will change your reference. You can at will rotate your reference. So if you kind of like look at a circuit where the reference is not, where your reference is not exactly 0 degrees, it's some other degrees, you can always rotate your reference. But the relative, if the circuit stays the same, the relative positions of all the and angles of all the other phasors will always follow the reference. So VR will remain in this position, VC will remain in this position. It's going to be just rotated by some angle, VL. Okay. So this is hopefully like the skill of drawing phasor diagrams for different situations and different references is something that you should pick up, like I said, and we will do multiple homework problems and examples as we move forward. All right. So this is it for this lecture, and see you guys next time.